Okay, so let's start our lecture today. So, yeah, I think last time I will stop where I think I divide the whole plane into like several regions, right? And then I think there is some identification between these regions here. So, yeah, I forgot like what exactly the identification is. Hold on. So, okay. So, okay. So I think for each one, right? So if you pick a point, let's say here, then when you are double and then you're okay, so what you really do is that because so when you focus on the first one, right? So what you do is that you focus on like the okay, so the angles of the points inside the first region are between like these and these two lines. So namely the thetas are between 0 and power 4, right? So when you double it, right? So it becomes power 2, right? 0 and power 2. So then that becomes your first quadrant. Okay. And then when you are okay, yeah. So when you are doing the flip, right? So actually it becomes yeah. So when you are doing the flip, so because you get negative power 2. Yeah, that's equal to negative 2 theta. That's equal to 0. Okay. So therefore, that becomes the fourth quadrant. Okay. Okay. So I think for number, if you go on number 2, then if you start with power 4, and then if you doubling it, oh, okay. Okay, yeah, it becomes power 2 and pi, right? And then if you take the negation, okay, so then it becomes negative pi, negative power 2. Okay. So this goes to the fourth quadrant. This goes to the third quadrant, and then this one, and this one, let's say power 2, c power 2, right? And then doubling. Wait. Hold on. Okay. Wait. Okay, 3 pi over 2 and no 3 pi over 4, yeah, so 3 pi over 2 and 2 pi, okay. Okay, so this goes to 1. Wait. Yeah, so this goes to 1. And then this goes to 2, okay. Yeah, I think that's the only choice, right? So 3 is between, so 1, 2, so this is 4. And then for 3 you get pi over 2 to 3 pi over 2. And then you get pi oh, 3 over 4, 3 pi over 2. Okay, yeah. So okay. So I think basically okay. So what about 5 here? So basically what you do is that you you are doubling. Okay, so when you are doubling, okay. Oh, okay. 5 pi over 2. So when you are doubling, so for here when you are doubling it, you are getting this like this 2 pi and then like okay, so it matches the first one. Okay. And then you take the negation. Wait, this is 2 0. Yeah, so and then you take the negation. So this again becomes becomes 4. Yeah, you're doubling and then you take the negation. So that's same thing for 6. If you compare this 6 and 2, so 6. So this is 5 pi. Oh, okay. Wait, not necessarily true. So for number 6, it's over this region, right? So number 1 expand is over this region. Number 2 expand is over this region. Wait, I think so. Okay. Okay. So okay. So this 6. Okay. This 6. Okay. Okay. Yeah. So okay. I think the idea is that, so for number 1, right? So number 1, it is like this angle. So after you double it, it matches the first quadrant, right? And then you do like a flip, and then you get the first quadrant. And for number 2, right? So number 2, when you're doubling it, you get the second quadrant, right? Because the starting point of the number 2 is at the ending point of the doubling of the number 1 doubling. So therefore, it goes on to the second quadrant, and then if you flip it, it becomes 3. So similarly, for this one, right? So this one, the starting point is like the ending point for number 2. So and then when you are doubling this one, then continuous goes, it goes on then wait. Yeah, so and then you like you increase like a 45 degree, then doubling becomes increase of 9 degree here. So therefore that becomes the third quadrant, and then you flip back become the second quadrant. So yeah, number 4 is the same thing. Yeah, so it should be the first quadrant, and then it goes back to the 1st quadrant. So it's like a cycle for 1, 2, 3, 4, right? And then for this number 5, basically you start the cycle again, right? So you start with the cycle again. So right, and then you increase. That becomes an increase of 90 degree, right? So therefore we get this 4 again, and then for 6, you should get 3 again, right? And then for 7, you get 2 again, and for 8, you get 1 again. Okay. So namely, yeah, okay. So namely, if I want to look for some canceling here, so what should I really look at? So if I were to look at some canceling here, where should I look at? So I think, naturally speaking, I think I should look at the place where they go for the diagonal entry, right? So for the diagonal one, I think basically there are, let's say 1 and 2, right? No, 1 and 3. So these 2 are corresponds to 3, 1. Okay. So okay, and then these 2 are corresponds to the 1s. So namely, I want to look for something like the points that's in this diagonal. Okay, like negative like negative 45 degree angle. Okay, and then these two angles, they could be result in some potential cancellation. Okay. Okay, so yeah, and also okay, so okay, um, okay, idea, so potential idea is that so looking for points or like symmetric, okay, points um, from these 4 and 8 and then relatively to okay relative to the point in like 2 and 6. Yeah. So okay, so let's bring our example in here. So yeah, so okay, so here if we were being bring into our lattice here, right? So let's just try to shrink it, okay, or maybe not to shrink, but okay. Right. So here. Yeah, so let's think about this example here. So what kind of symmetry do we get in this case? So yeah. Hold on. Yeah, so there do have symmetries in these two right? In like this 4 and 8, right? So we will draw like the rectangles, right? So yeah, I'm trying to draw like the rectangle lattice. So I'm kind of assuming that this omega 1, so this is like omega 1, right? And then this is like the vertical one is like omega 2, right? So omega 1, they are like positive reals, okay? And omega 2, they are in like the imaginary line, okay? So now, okay, so here, so I'm just assuming that kind of like this omega 1 is longer than omega 2, right? And also, let's say, okay. So maybe, okay. So yeah, I'm thinking about this, these two angles here. Wait. These two angles. Okay. Yeah, so if I'm trying to look at the points on these two here, right? So what I'm thinking at is that we can like keep increasing and increasing, right? Okay, so and then for these points on these two, I think the idea is that this omega 2 has to be somehow bigger than omega 1, right? Right, so right, so if you fix omega 1, oh, okay. Yeah, so omega 2 has to be bigger than omega 1. Or like the copies, I'm thinking about points in the lattice, right? So in lattice, like if you have like the you have like let's say the points are like n omega 2 times m omega 1, right? So where omega 2 is like the y value, like the y value has to be bigger than the x value for it to rise to 2, right? Another positive, yeah. So therefore, yeah. So therefore, the n omega 2 must be bigger than this m omega 1. And also, yeah. Let me think. So, yeah, but. Yeah, so why they cancel out, or why it's the finite sum, right? So over this lattice. So um, okay, I'm thinking of like, because the points in like 1/8, they are, because when we think of the analysis, right? So the points in like the 1 and this 8, they are like really similar to each other, right? So you just take a symmetry around the complex conjugate, right? So when you're taking the complex conjugate, then you should wait. So I don't think I'm allowed to take the complex conjugate in this scenario. So yeah. So but I mean in this case, it seems that I'm allowed to take the complex conjugate, but in like more general example, right? So like only I think there will be a symmetry. Where is the symmetry? So we have omega 1, omega 2, then wait, can I actually show that if I do some rotation? Wait. Wait. Yeah, so I'm thinking about like, because I think you can also define this. So if you rotate by each element, if you rotate each element by some by some angle, right? Wait, actually, um, yeah. So if you rotate the whole lattice by like an angle, yeah, and then you show like the sum of the rotated lattice converge, then does it imply that the original lattice converge? Okay, so let's start with the thinking that if I rotate this guy by like to in the order that these lines, this omega 2 lies on this diagonal, and then this omega 1 it lies on this diagonal. Okay, then what will happen? So this is like the omega 2, like say e to the I theta, like e to the I power 4. Okay. Yeah, and then this is like sorry, negative. Yeah, negative. And then so this is like e to the negative I pi over 4 times omega 1. Okay. So then okay, so let me try to draw this. So the lattice becomes in this direction, right? Okay. 1, 2, 4. Yeah. So 1, 2, 3, 4, 5. And then it goes in this direction. Then the parallel. Okay, so let me relabel it. So we are interested in this 2, 6, right? Okay, and then this 1 and 4 and 8. So this is 8. And then this is 4. So the points are not exactly the same. Yeah, I think on the one hand you are starting with omega 1 and then you are adding omega 2, right? And then So and then for this 2, right? So you are starting with omega 2. Wait. I think that's about like the ratio of this of this omega 1 and omega 2, right? So and because for each letters you are having this m omega 1 plus n omega 2, right? Let's call it omega 2 there, right? So let's denote it by omega 2 there. Okay. So this is omega 1 2 there. Okay. So yeah. Okay. And then so let's consider the special case. Okay. Where this omega 1 is equal to e to the yeah, so okay. Okay, so let's focus on this okay, so let's focus on the potential cancellation for this 2 and 8 case. Okay. Okay. Sorry, 8 and 2 case. Okay. Yes. So let me think. So for you to be 8 case, right? So namely so in 8, so for the points in so in 8 we must have that this m so namely this m omega 1 and this n omega 2. It cannot go beyond, right? It cannot go beyond. So what do I mean by it cannot go beyond? So namely this I think the modulus of this n omega 2 there must be less than, does it have necessarily equal to? Okay, less than equal to this modulus of m omega 1 2 there. Okay. Yeah, so this is like the height. Yeah, so this is like the height, and this is like the forward direction. Yeah. And also m and n are positive, right? Okay. Yeah. Oh. Okay. Wait. This m must be positive. Yeah, m and n must be positive. M must be positive. Wait. Yeah, m and n must be positive. But not 0, yeah. Okay. And then so what happened for it to be 2, right? So for it to be in 2, you must have like it's flipped, right? So modulus of omega 2 tilde should be bigger than or equal to modulus of m omega 1 tilde. Yes. And also you have the n must be bigger than 0, and then this m must be negative, right? Less than equal to 0. And then when this m can be equal to yes. So when you fix the m, right? So when you fix the m, so there is finally many n that lies in between these. So if you fix n, let's say bigger than 0. Yeah, so this m cannot be equal to 0. Otherwise, this n has to be equal to 0, right? And then it cannot happen. So yeah, so this m has to be bigger than 0. So for it to lies in the region 8. So if you fix that big m, so then for each m there is only finally many n such that this is satisfied, right? And then and all the rest they lies in this, yeah, right? So for example, the m, so there's like a conjugate point. So there is like a negation with m, right? So for example, we fix m equal to 2. Then there's a corresponding point here that corresponds to this negative 2, right? And whatever, like you have the n omega 2 that's less than equal to this m omega 1, there is this corresponding point that lies in this third, like number 3 region. And then once you go above it, right? So once you go above it, then all the rest points they all lies in this 2 region. So I'm thinking. However, there could be more and more points, right? Because for each m, yeah. Okay, I think maybe I want to stop here. Okay. Okay, yeah, I'll just stop here today and then I'll continue next time.